and optical implementations of quantum information tasks. His current research interests include quantum resources and also optical and atomic implementations of quantum information tasks and protocols. Barry is a fellow of the Institute of Physics UK, the Optical Society of America, the Australian Institute of Physics, and the American Physical Society. A past president of the Australian Optical Society, current secretary treasurer of the American Physical Society topical group on quantum information, vice chair of the Canadian Association of Physicists, Division of Atomic and Molecular Physics and Photonic Interactions, a member of the American Institute of Physics Education Advisory Committee, an editorial board member for both PRA and the New Journal of Physics, and advisory board member for optics communications. In addition, Barry has served and is serving on numerous conference committees for the American Physical Society, the International Society for Optical Engineering, and the Optical Society of America, and various quantum information conferences. So this is where the short bio ends, but then of course, I'm sure the point that we all take home is that, Barry is one of the most accomplished quantum information physicists that we know, and it is a great pleasure to have him here with us in this conference in spite of the time difference. So Barry, over to you. I think you are physically giving the talk then, so please, over to you.
Thanks. Thanks very much, Urvashi, for the very kind introduction. I sent over a link for the pre-recorded version. Is that from the organizers?
Yes, so Kavita has that, and yeah. Kavita?
Yes, it will play shortly.
Right, great. We don't have the volume.
Thank you very much for the kind introduction.
Barry, while we wait for the digital avatar to kick in, hope you're doing well.
Everything is good.
Yeah, great.
I'm
yeah.
nervous that it's not going to.
I think it will. It's just a very surreal experience. It's a superposition of the two of you.
Yeah, very quantum talk.
Yes, it's as quantum as it gets, and of course, we know you well enough.
I see myself talking. I just don't hear much.
No one does right now. I think we had a weather change from when you recorded the talk and when currently, right? No jacket right now, huh?
Yeah.
We're going to talk about.
Yeah, we tested, everything worked fine. So I don't understand what's going on.
Yeah.
I think there are just a couple of glitches. The student volunteers are looking into it.
Do you want me to talk live while they figure it out?
Well, we still need the slide changing, right? Well, you should talk live for sure. I mean we are already, I think we're already talking, so.
Yeah, you're right.
Yeah. Is this a new experiment, Barry? We are doing? Trying to get the link? No, okay, yeah.
No, it's
the link, the link, using a link while you're actually here. I mean, are you just testing it out to see if it works in your absence as well? Or, I mean.
No, I've done it before.
You've done it before as well. That's very interesting. I mean, we should try this.
Yeah, well, I've done a whole course now teaching with tutorials and sending links. So we just turn on Zoom and record it, and then it plays back.
Yeah. So what the student is doing is obvious. He's going to reshare, right? I mean, that always works, at least switching it off and on.
Well, what's worrying, it says live on YouTube, but it could be downloaded.
Yeah, we are live on YouTube.
Oh, I see. Okay, well, this is a little
Yeah, we are
embarrassing.
live on YouTube. So yeah, it's whatever you say, it's on YouTube. Yes.
Yeah. Okay. Well, maybe I don't know what to do.
So
I'll just.
do you want to send the talk to one of the people and we can, okay, I think we are trying it again. And
Yeah, they have it. Everything is there. So, but I'm not sure what they did with the link.
Thank you very much for the kind introduction.
Yeah, it's working.
And I'm pleased to be able to give you a talk on some very recent work that my student Shalini Karavade and my postdoc Abhijit Alais and I have been working on. Both of them are here. You can see them present. And as this is joint work, we're all going to present. I will do much of the presentation, but each of them will present one slide. They've done the most of the work, and it's fitting that they present part of it. You get a chance to see all of us who put this work. We're going to talk about observing a changing Hilbert-Space Inner Product, and I'll explain to you what that means, and the motivation behind this will become clear. It's very much related to this giant topic of PT symmetric evolution. So evolution that's generated by PT symmetric Hamiltonians. Okay, so let's discuss. Here's the table of contents that explain how we're going to proceed. So we'll introduce the topic, give some background, and then we'll go through some slides that tell you about the approach we're using and the results as we go. And then we'll come to some conclusions. I'm very reachable. You can see I have a strong social media presence, and there's a number of different links if you want to find me or contact me. And then the beautiful picture on the right is Calgary on a sunny day with the snowy Rocky Mountains in the background and the beautiful Bow River flowing through. So let's get down to business. In this slide, I'm going to tell you about the context for our work and the aim that describes what we're trying to achieve and what we in fact have achieved. The context for our work really comes down to the basic mathematical properties of quantum mechanics that we learn in university, undergraduate level, and we take for granted. I'm just going to indulge at the moment in going through this very basic quantum mechanics because the inner product is part of the story, and it's something that we tend to take for granted. But there are subtleties to the inner product, and these subtleties have to be clarified in order to grasp how the inner product can change and how it relates to PT symmetric quantum mechanics. So we learned that quantum mechanics is about state, subject, which we to ignore, can't afford to ignore, is the inner product. I think of as the cats, the states that we use in quantum mechanics, like the psi cat. The inner product is a sesquilinear form that maps a pair of cats, so a pair of elements of the vector space, into a complex number, such that, and the way we can think of it loosely is the two elements of the vector space are two cats, the phi cat and the psi cat, and then it's mapped into the inner product where we make phi into a bra, and psi is still a cat, and then we have our calculation to do it. And I'm not going through at the moment how the calculation is done, but if it turns out that we represent phi and psi by complex vectors, so if it's a qubit, a two-component vector, spin half system, psi is a two-component column vector with complex number entries, phi cat is the same, and then we make phi bra, we turn the column into a row by transposing, take the complex conjugate of the elements, and then use the regular dot product that we would do for complex vectors. And now some interpretation, which we need to be clear on. So the ket psi is in our way of thinking, a description of the preparation. What kind of description depends on how it's represented. So you can think of position representation, Fock number representation, spin representation, and those determine exactly how the description is written. And the phi bra is the description of measurement. So in the pure state projective measurement case, we think of states as being kets and measurements as being bra. And then the inner product is just the bra applied to the ket. And that tells us the probability amplitude for a measurement outcome. Prepare the state psi, measure with respect to observation or observable phi, and then the probability amplitude is a complex number. The mod square gives the probability in a strict sense for that event occurring. Surprisingly, despite quantum mechanics being more than 100 years old and almost 100 years old in the current formulation, the changing of the inner product during the evolution is a topic that hasn't been addressed. But as we'll show you, it arises implicitly as we, arises implicitly in the PT symmetric analysis. So that takes us to our aim. And our aim is to establish a framework that is wholly consistent with quantum mechanics for changing the Hilbert-Space inner product between preparation and measurement. And this presentation necessarily becomes quite mathematical because we got to make sure everything's consistent, and we have to make sure it's consistent in the strictest sense with the requirements to have quantum mechanics properly established. Why are we doing this? So on this slide, I'm telling you about the motivation and importance, and I'm just posing 3 rhetorical questions. First of all, can the inner product be modified in a way that's consistent with standard quantum mechanics? And this question is important because there is previous work. So we give a couple of references here, one to Scholz, Gehr, and Hahn, and another one to Mostafazadeh, where they do talk about modifications to the inner product. They do not sufficiently address the consistency question, but they do set the basis for the kind of analysis that needs to be done. So can inner product change be made consistent with standard quantum mechanics? Why does the question even come up? Because if it's not consistent, it could be advantageous. We give a couple of references, reference 2, John et al., and reference that's on cloning and the idea that somehow by changing the inner product, we could violate the no cloning principle. And reference 3 by Bender, Brody, Jones, and Meister addresses the question of whether this changing inner product or PT symmetric quantum mechanics could somehow help with computation. And then the final rhetorical question on this slide is about observing exact PT symmetry. Is it observable? And there's beautiful work by Brody where he shows that in a closed system, exact PT symmetry is not observable. And then there are analyses of studying exact PT symmetry by open system experiments, and those aren't yet placed on a firm basis. So even the question of whether exact PT symmetry, hence changing inner product, can be observed remains open. So in summary of this slide, can the inner product change and equivalently PT symmetric Hamiltonians be consistent? Is there an advantage to changing the inner product or changing to PT symmetric systems? And is it observable? And so those are open questions that we address here. So our claims are that we have developed a framework, so a proper, rigorous mathematical framework, fully consistent with quantum mechanics for changing the Hilbert-Space inner product. And by changing it means that during the time scale of an experiment, from preparation to measurement, the inner product can change, and it can do so in a way that's consistent with quantum mechanics. Furthermore, we show that this change in inner product is fully consistent with and implementable by applying a quantum channel in the strict sense, so a completely positive map with conditions on the trace, and we'll make that clear. We have connected our framework to the dynamics of open PT symmetric systems, so that connection between the changing inner product and the open PT symmetric systems becomes clear. And finally, in order to bridge the gap from theory to experiment, we have devised a qubit protocol that would enable change in inner product of a qubit system. Our work introduces some methodological novelty. First of all, we, unlike previous work on PT-symmetric systems, we're bringing the full force of C-star algebra to bear on this problem. So in order to make sure it's formally valid, correct, consistent, and that it's operational, that it does tie in properly with notions of preparation and measurement, we use the C-star algebra framework and explain with commutative diagrams how different notions connect through this framework. We have also employed the freedom that exists between in choosing different representations for Hilbert space to construct the quantum channel to implement the change. So by recognizing that the representation has some freedom in which choice is being made, it allows us to construct a quantum channel to do so. And finally, we show how to operationalize PT symmetry via this change in inner product. So this slide captures or shows the headers for 4 key papers. And so just to highlight the background and explain what's going on, I'm mentioning these papers. They're easy for you to look up and study in detail. On the upper left, you can see the Bender and Butcher paper, which is the seminal paper from 1998 that introduces the idea of PT symmetry, the idea that quantum mechanics doesn't require self-adjoint or Hermitian Hamiltonians, but rather PT symmetry that gives non-Hermitian Hamiltonians real spectra could lead to a consistent formulation of quantum mechanics. And this is the kind of thing that we're addressing here, that by understanding it as an inner product change, it kind of puts this whole mystery onto, we're demystifying it. It makes it all very clear. Below you can see Mostafazadeh, who recognized the connection between Bender and Butcher's idea with standard quantum mechanics. So his paper is very clearly titled Exact PT Symmetry is Equivalent to Hermiticity. So he establishes the notion that there is a transformation that makes non-Hermitian Hamiltonians Hermitian. On the upper right, Brody had a paper called Consistency of PT Symmetric Quantum Mechanics. And that paper was important because certain misconceptions arose over the years that, as I mentioned before, led to expectations of advantages beyond standard quantum mechanics. And Brody showed the consistency to show that quantum mechanics and PT symmetric systems are equivalent. And finally, there are a set of experimental papers. This one is one that I was involved with on experimental quantum cloning in a pseudo-unitary system. And it shows the experimental approach to realizing PT symmetry. And these experimental approaches are very instructive because by going through them and studying how to actually work in the lab to simulate PT symmetric systems or equivalently inner products, it's helpful to do the experiment. And moreover, in this paper, we've made clear we explained it in a colorful fashion as 2 universes. And so the idea is that we imagine that there's 2 parties, Alice, Bob. Alice lives in the universe with standard quantum mechanics. Bob lives in a universe where quantum mechanics is modified to a PT symmetric system. And then Alice can send stuff to Bob through a wormhole between the universes. Bob can do stuff and send it back. And so occasionally during this presentation, I'm going to fall upon this 2-universe description because in some colorful way, it can make clear the tough mathematical concepts that arise. And now I'll pass over to Abhijit to talk about slide 7.
Thank you so much, Barry. In this slide, I will go over some of the basic mathematical concepts in PT symmetric quantum mechanics that we will need to explain the approach and the results. So first of all, the definition of PT symmetry. In an abstract way, we can think of P as just a linear isometry, that is a unitary operator, and T as an antilinear isometry, that's an anti-unitary operator on a Hilbert space edge. and we require that both of them square to identity and that they commute with each other. This is motivated by particle physics, but in our it's motivated by the parity and time symmetries in particle physics, but in our talk we will keep them abstract. So a PT symmetric Hamiltonian is a Hamiltonian that commutes with the PT operator. So PT is an antilinear operator, and therefore just the commutativity condition does not guarantee that Hamiltonian H shares an eigenbasis with the PT operator. And that is where the concept of exact PT symmetry becomes important. So if a Hamiltonian H commutes with the PT operator and additionally shares a complete eigenbasis with the PT operator, then we call that operator an exact PT symmetric operator. Such a Hamiltonian H can be shown to always possess real eigenspectrum. This has been done already. One of the important properties which we leverage in our work of exact PT symmetric Hamiltonians is that if H is defined on a finite dimensional vector space, and if it is diagonalizable on top of being exact PT symmetric, then we can always find a positive definite operator eta that satisfies eta inverse H dagger eta equal to H. This condition is called quasi-hermiticity in the literature and is closely related to the hermiticity. So these are the basic concepts in PT symmetry which we will require later. And now Shalini will explain to you a few basic concepts in C-star algebra.
Thank you, Abhijit. So now I'll briefly explain the C-star algebra formalism of quantum mechanics that we'll be leveraging in order to operationalize changing inner product. So the operators of a quantum system can be shown to form a C-star algebra, which is essentially an algebra with a star operation that is an anti-linear involution. So observables of this quantum system are nothing but self-adjoint operators under this particular star operation. And any positive operator of the algebra A are operators of the form A star A for any operator A in the C-star algebra. So the states in which we can prepare the quantum system are represented in the C-star algebra formalism as linear functionals acting on the C-star algebra A with the following properties. The first property being the state maps any positive operator to a positive number, and the state maps the identity operator to a number that is less or equal to 1. And all the C-star algebras that we are considering contains the identity operator by default. So the C-star algebra formalism is somewhat an abstract representation of a quantum system. But thanks to the Gelfand-Naimark-Segal construction, we can represent a C-star algebra of operators onto a Hilbert space. So this representation is given by a mapping that we have written here as pi. So pi maps the operators in A onto bounded operators on a Hilbert space B of H with the property that pi of A star is pi of A dagger. So the star operation maps to the dagger operation in the bounded operator space. So this star preserving mapping in turn provides a representation of the states of the C-star algebra of the quantum system, on B of H again. So that's familiar to us in the form of density operators. So any density operators operator in B of H gives rise to a valid representation of a quantum state in the set of states S. Further, we can also see that pure states of a quantum system, the states in S that cannot be represented as convex combination of any other linear functionals, are representable by rank 1 density operators in B of H, which has a further representation at the Hilbert space level as the kets, which we are most familiar with. Also, we see that the GNS construction is not unique in any sense. We can choose to represent the C-star algebra on different Hilbert spaces, like the ones we have shown here, onto say, two different Hilbert spaces and the corresponding bounded operator spaces B of H and B of H prime. The corresponding mapping we denote by pi and pi prime. But these different representations are observationally indistinguishable in the sense that any expectation value of an observable that we compute with respect to any valid state of the quantum system by choosing one representation or the other always gives the same value. So there is no way to operationally distinguish that different representation that we choose for the C-star algebra. And we'll be leveraging this change in the freedom in representation provided by the GNS construction in order to explain the idea of changing the inner product. And in order to do so, I pass the screen back to Barry. Thank you.
Okay, thank you very much, Shalini and Abhijit, for clear explanations. And I'll jump back in, building on that foundation. So the point of this presentation is changing the inner product. So let's now explain exactly what we mean by changing the inner product. So at the bottom of this slide, in the red block, we make it clear. Let me build that up. So first of all, we need to discuss the metric operator. And the metric operator is a bounded operator. Now, we think of it as being on the Hilbert space, but for technical reasons, the metric operator only needs to be defined over a dense subset of the Hilbert space, which doesn't affect us for this analysis, but that's the technical definition, that the metric operator is positive, that it's self-adjoint. Okay, so now we have that definition of the metric operator. And any eta that satisfies that can serve as a metric operator. So in this next slide, we have the Hilbert space with the modified inner product. And remember that the Hilbert space is the pair, the vector space and the inner product. So when we modify the inner product, the vector space does not change, but the inner product does. And the inner product is kind of like, if you think of the vector space as kets, the inner product tells us how to turn kets to bras. So the way we turn a ket to a bra changes, and we index that by eta. So the eta subscript turns out that by choosing different metric operators, we have different ways of turning kets to bras. So we defined earlier the inner product, and this explains the modified inner product. So that script I subscript eta maps the vector space Cartesian product with the vector space to complex numbers, but we insert an eta. We turn phi to a bra, psi stays a ket, and we insert an eta in between. So it's like if phi is a row vector and psi is a column vector, eta is a matrix. And so this insertion of eta can capture all possible allowed changes of inner product. Now that we have that change in inner product, that will change representations on H eta, that Hilbert space. So as we've just heard, pi is a representation, it's not unique. So we can consider a representation of the C-star algebra onto the space of bounded operators, and we'll index it by eta. So if we take an operator in the operator A in the C-star algebra given by calligraphic A, then if pi of A is the trivial case, that eta is an identity, then the new representation, pi eta, is just given by the representation of A, and then it's sort of conjugated. We have an eta the minus a half on the left, eta the half on the right. If eta were unitary, which it isn't, we could call it conjugation, but it looks like that. And once we have that formalism in place, then we can talk about a change of representation. So the change in representation, given pi, goes to pi eta. That change in representation is carried by r eta, and that's the one that just sandwiched pi of A between eta the half on the right, eta minus a half on the left. So now we have an idea of how to use eta to change representation. Given that, we're now ready to define the change in inner product. And so that's given by a calligraphic I. So we're using calligraphic I for the change in inner product. The script I, the change in the Hilbert space, including the change in inner product. So the calligraphic I sub eta carries the Hilbert space for trivial eta to a non-trivial eta by carrying any state psi in the vector space to itself, but modifying the inner product as we've just explained above. Essentially, it's to insert the metric operator. So once we know this, then we can start getting to the operational side. So in this slide, I explained to you how the inner product change can be implemented and observed. And for this purpose, we use what's known as a commutative diagram in structural mathematics, also known as category theory. And so the goal here is to explain to you how the inner product change can be executed by a channel. So on the lower left, you can see script H, the Hilbert space, and then that's carried by I eta to script H subscript eta. And as we just went through, the calligraphic I sub eta keeps the vector space the same, all the kets don't change, but the inner product changes. So now what we want to do is turn that into figuring out how to use channels. So here you can see a lift operation. And the lift operation you can think of as follows. The Hilbert space comprises kets. The lift allows the bounded operators to form, which can be thought of as linear combinations of ket bras. So a ket bra forms the basis for operator space. And then given those operators, we're able to describe the states. And to go from bounded operators to states, we have an operation that's known as sharp. And sharp subscript pi carries operators into states, which we've discussed earlier. Now, moving to the right, so in the lowest rung of this ladder, the calligraphic I sub eta carried the Hilbert space to the new Hilbert space, i.e. changed the inner product. But once we do the lift operation into the operators, then we can describe that mapping by E tilde eta, which carries operators to operators, and I'll explain in a moment. And then doing the sharp operations, we're then able to describe how they act on the states themselves. And you can see at the very top, there's E subscript eta, which is the mapping of states to states by a channel. Let's take the middle rung of this ladder, the E tilde sub eta, and understand what's going on. So on the right, what we discover through the mathematical analysis is the E tilde eta carries an operator to an operator as follows. Given an operator M in the bounded set over Hilbert space, bounded operators over Hilbert space, E tilde eta is just multiplying the operator M on the right by eta. So that right side multiplication corresponds to what the channel needs to be. So that's mathematically fine, but not exactly what we need to make these, to be able to make it observational by tomography. So we recognize that E tilde eta can be written as the composition of two operations, F eta on the right followed by R eta. R eta we saw on the previous slide was the change of representation, and the F eta is defined to be a mapping that looks very much like E tilde eta, but instead of mapping M to M eta, it maps M to E to the half, M eta to the half. And so operationally, that's equivalent to E tilde eta. What it means is that if we define the channels, or we establish the channels in terms of E tilde eta or F eta, there will be no observational difference. And it's more convenient to work with F eta. And the reason, which you can see in the bottom block of this slide, is that process tomography can be used to obtain eta. So this is now, there can now be a channel tomography process in order to be able to estimate eta. And since eta is identified with the inner product, by estimating eta through process tomography, we then use the mapping to figure out what the inner product changes. Okay, so that slide explained how operationally we do the inner product change. Now we need to connect it to this vast field of studies on PT symmetric Hamiltonian dynamics. So for that, let's understand what the PT symmetric dynamics is about. So as you heard earlier, we can introduce the PT symmetric Hamiltonian, so it doesn't have to be self-adjoint or Hermitian. It has a real spectrum. It's got the commutes with the PT operators, which are generalizations of parity time, and also a time of evolution. So given HPT and given T, in our process, we use that to construct the effective unitary. It's not really unit. So if HPT is not Hermitian, then UPT is not unitary. But we do the same process. HPT generates the dynamics, so we exponentiate. And so what you see in this expression looks like regular quantum mechanics, except this is not Hermitian or self-adjoint. Therefore, this is not necessarily unitary. We do the exponentiation, and then we implement the following map. Now, if UPT were unitary, we don't need this kappa term, and then this conjugation of rho, the representation of the state, would give the new state time t later. But because it's not unitary, there's a multiplier of kappa, and kappa needs to be some number between 0 and 1 for this procedure to work. So we use the calligraphic U subscript PT to represent that overall unitary conjugation with the multiplier by a kappa. In order to explain how to implement this dynamic, we just take into account two facts. So one fact is that there exists an eta, and the eta is constructible, so that given any HPT, there exists some eta such that the dagger of HPT is given by eta HPT eta inverse. So that can be calculated, and that guarantees that HPT, which is a bounded operator in H eta, so that's the H but with the modified inner product, is Hermitian. Now I'm using the terms Hermitian to keep it user-friendly, but just to be clear, in the infinite dimension Hermitian, we have to be careful about the term Hermitian, so self-adjoint, but just to keep it friendly, we're using the term Hermitian here and there. Now the second fact is that the unitary operator, UPT, and it's unitary if HPT is Hermitian, is related. So basically the mapping of the PT symmetric version versus the standard quantum mechanical version. So the standard quantum mechanics is on the left, that's the UPT in B of H. And on the right, that's the UPT in bounded operator on H eta, the modified inner product. I told you I would talk about two universes. So let me just explain briefly the two universe idea. So Alice lives in a universe with ordinary quantum mechanics. So UPT refers to the operation in her universe. Bob lives in the universe with modified quantum mechanics, and that's described by the eta. And so the way you can understand this expression is Alice wants to execute UPT, which is not a unitary transformation. It's one generated by a PT symmetric Hamiltonian, but she sends to Bob through an inner product changing process. That's the calligraphic I eta on the far right. That acts on it to send it to Bob's universe. Bob then applies his unitary UPT, and because it's generated by Hermitian HPT, and then he sends it back to Alice. And then Alice gets the benefit that Bob was able to, by sending it to Bob and getting it sent back, this PT symmetric Hamiltonian evolution was performable. And the process is explained below in this commutative diagram, where you can see B of H. So those are operators in Alice's universe. Those are the states that are related to those through the sharp operation under some representation pi. Then there's a channel operation. So Alice sends to Bob in his universe through the channel. The tilde represents the method. So the states themselves are sent through the channel E subscript eta. The mathematical description of how the operators change is given by E tilde eta. They map over, and then in Bob's universe, there's the states and the B of H eta. The states themselves don't change, but the inner product has changed. That then goes through, the states go through that UPT transformation. Mathematically, that's the operation generated by exponentiating HPT. And then there's sending back. So it's kind of the counter channel. And you notice here that the counter channel is not the inverse of the original channel. There's some modification due to the norm of eta inverse. And that modification is kind kind of what saves us from counterintuitive or counterfactual operations. So the idea that the no cloning theorem can be violated or there could be computational advantage is removed because the effect of this operation is to delete things. So instead of violating the no cloning theorem, cloning can be possible some of the time, but it's random when it works. And so quantum mechanics is preserved by that fact. We have a way of simulating with qubits. And so we don't put all the details here due to limited time, but essentially we've designed an experimental procedure that allows a simulation of all this by taking the qubit, embedding in a qubit. So rho is a 2x2 matrix. We then have a 3x3 matrix. And so you can think of like a 3-level atom. The lower 2 levels are the qubit, and the upper level is unoccupied and of course no coherence. Then there's the unitary map in the qubit space, so the qubit unitary map, which changes that matrix to the f eta of rho. F eta we defined on the previous 2 previous slides ago. So it does that operation. And then it turns out that the 3rd level gets occupied and there's some coherences. But when it goes back to Alice, Alice only cares about the qubit subspace. So there's a projection that turns those to zeros, executes the f eta of rho, and the effect of the projection is to make it work sometimes randomly. And then we've devised a verification procedure using channel tomography to show that that works. And the advantage of doing this, instead of doing something like a Stein spring dilation, is it turns out to be experimentally very feasible to be able to convert this to a qubit simulation. So the upshot of this slide is that we have a way of doing qubit, basically simulating PT symmetric dynamics or inner product change just using a single qubit. And then in conclusion, we've shown that the inner product change is consistent with standard quantum mechanics. We have shown that the change in inner product is equivalent to a quantum channel, followed by change in representation. We have shown that the change in inner product can be leveraged to implement PT symmetric dynamics. And we have shown that a qubit PT symmetric can be simulated with a standard single qubit. And finally, the real take-home message is that we have succeeded in demystifying a lot of the PT symmetric dynamics, and also discovered that the taken for granted inner product in quantum mechanics can be very interesting if it's allowed to change. Thank you very much for listening, and we look forward to questions.
Thanks a lot, Barry, for this very nice talk. So we have now some time for questions. So are there any raised hands? Yes, so Satvik Singh, can you please unmute and ask?
Hello, am I audible?
Yes.
Yeah, so first of all, I would like to thank you for a very succinct presentation. So I have a couple of technical questions. First of all, about the definition of the PT symmetric Hamiltonian, are we assuming that it is bounded? It is a bounded operator on the Hilbert space? I mean, in the
yes.
entire analysis?
Yes, Abhijit or Shalini, do you want to comment on that?
Yes, I can take this question. The exact PT symmetric Hamiltonian has a real spectrum, so we can put bounded from below condition on Hamiltonian, just like in standard quantum mechanics. The PT symmetric broken Hamiltonian, however, does not have real spectrum, so that kind of condition we don't put. But our work focuses on exact PT symmetric Hamiltonians, and therefore we can put that condition.
But I mean, it's still bounded from below. It can be unbounded from above, right?
Yes.
So,
right.
I mean, there are domain considerations and everything that come into picture while considering this. I mean, it's not defined on the full Hilbert space. You have to kind of restrict it to a dense domain or something like that.
Yes, that is correct. We treat it the same way as it is done in standard quantum mechanics in that case.
Right, and the other question is about the metric operator itself. So in the definition, you say that it is a bounded operator on a dense subset of the Hilbert space. Am I correct?
Correct. So that goes back again to a standard definition, and that avoids things like singularities.
Yeah, I mean, so what is the significance of restricting the domain to a dense subset? I mean, since it's a bounded operator, can I not just uniquely extend it to the entire space by using the bounded linear theorem? I mean, what is the significance of restricting it to a dense domain? And in that case, if we do restrict it, the definition of the modified inner product. So in that inner product, the vectors are from the entire space, right? But then the eta is acting on a vector. So the vectors will then be restricted to the domain, the dense domain itself, and then we'll have to kind of extend using continuity this definition to the entire space. I mean, I don't understand the significance of the dense domain in the definition of the metric operator.
Your intuition's good. You can take it defined over a dense subdomain and then extend it. And I think the point is, it's like making a mesh. You know, if you make a mesh, you can then interpolate, but it's kind of a coarse graining effect. So the way I see it is, I don't actually know really why it's defined in that way, but my intuition is that by doing so, it avoids singularities. Then when we can do what you say, you just define it over a dense mesh and then do some kind of continuity rule to extend to the full domain.
Okay. Thank you. Thanks a lot.
So the organizers have just informed me that we are running a little late. So we will have time for 2 to 3 more questions. So the next in line is Professor Dipankar Home. Professor Home, can you unmute?
Yes. Hello, Barry. Thanks for your talk, instructive talk. Hi. So just a couple of questions. You mentioned about in that context of that two universe scenario where you have the PP symmetry in one wing and or standard quantum mechanics in the other wing, about no cloning theorem being violated a number of times, but randomly happening. Now, what happens to the no signaling condition in that case? Or can you expand on that a bit? What you meant by it's violated a number of times, but randomly means it's uncontrollable way, means just the fidelity bound or so on. Because we have the fidelity bound from no signaling, so no cloning related. And I vaguely also remember, although I have not followed the literature in detail, if you just have two PT symmetric quantum mechanics, if you formulate EPR Bohm scenario in the PT symmetric quantum mechanics context, about the no faster than light condition, what's the status? Can you comment on that?
Yeah, sure, great. So that's part of the motivation for our work is there was work in the past that claimed violations of no cloning, but yes, I'm sure you know that
no and also no theorem, signaling condition also for PT symmetric. There were some discussions because with non-Hermitian, there were theorems proved in early 90s that if you have non-Hermitian operator in the normal EPR Bohm scenario, it allows for faster than light signaling. If non-Hermitian operators with distinguishable non-orthogonal eigenstates, which can be discriminated to certain points. So can you comment on that in the modern context?
Sure. So the point was there has been work in the past that suggests that the no cloning theorem is violated, and we don't take that view. Part of the motivation of our work is to prove that all this PT symmetric stuff is completely consistent with quantum mechanics. So the way to think about the seeming violation of the no cloning theorem, so as you know that even if cloning is not allowed, some partial cloning is allowed, and that can be manifested in 2 ways. You can either have imperfect cloning that then meets the fidelity limit, or you can have random instances of perfect cloning that are heralded and then it fails other times. And so both of those are consistent with the no cloning theorem. And then what we discover in our construction, and this is our colorful 2 universe language. So what we imagine is Alice can't break the no cloning theorem, but she sends stuff to Bob. And then in Bob's universe, he'll take 2 non-orthogonal states and make them orthogonal. Then he can clone, and then he sends them back to Alice's universe, because in his universe, they're orthogonal. But when he does so, the effect of the channel in between is to delete random copies. And I saw a message here on chat also about the kappa. And Urbashi, it's not your kappa, it's a different kappa. So the effect of this kappa is that it winds up deleting randomly. So Professor.
Okay. So the role of that deletion is crucial when you reverse channel.
Yeah, the deletion. Yeah, exactly. When there's the change of inner product and the change back, deletions occur during the change of inner product. And you can see it as follows. When you change the inner product, you then change the norm. And when you change the norm, this can be a noiseless loss mechanism in a physical sense.
Yes,
and then your questions about signaling and all this also fall into play. That what we find is that the change of inner product implies the change of norm, and then that preserves all of quantum mechanics. No cloning, signaling, everything then holds.
But no signaling still, but signaling can occur sometimes, but that's cannot be in a controllable way.
That's what I suspect, but we haven't studied that case.
Okay, that would be interesting, because if you know, if signaling occurs, that it can occur sometimes, but not in a controllable way. And there's something analogous to deletion in your two universe picture may also exist.
Yes, there's something analogous to deletion, and the way, and that's why we went to some rigorous mathematical foundations, because the idea was exactly to make this clear. There is a lot of confusion out there, and by going to a structural mathematical argument, I think we've made clear that even using this PT symmetric version preserves all these beloved properties of quantum mechanics.
Okay, so that will be interesting to study. So that what is the analog of deletion when in the context of this no signaling condition and the preserving.
Yeah.
So for the interest of time, I think we will stop with Usha Devi's question being the last one, please.
Hello. Thanks, Barry, for a very interesting talk. So my question is something to do with a 2-qubit PT symmetric Hamiltonian. It has 6 parameters in general. That is, if I write a 2-qubit non-Hermitian Hamiltonian, there are 6 parameters. And if I take, say, for example, Lorentz transformation and its representation, a two-dimensional representation, which is non-unitary. Representation of Lorentz transformation is non-unitary. It has 6 parameters. So are there any connections between PT symmetric operation and non-unitary Lorentz transformation representations? Because this would connect PT symmetric operations straight away to local operations on qubits. There is some difference. I'm just curious if there could be any connection like that.
Yeah, I haven't thought about it. I know what you're talking about. And maybe, so in this colorful 2 universe kind of way, maybe it's even possible to think of the, so the change of inner product is given by a channel. That's what we prove. And then that channel could be what you described, a Lorentz transformation.
Yeah, because
so
there
I could
is
just
also,
imagine that Alice and Bob are related in some relativistic sense. I get your point.
Yeah, but also there is in your Lorentz group non-unitary transformations, one can find a kind of metric there too, and metric transforms it into some kind of a real complex conjugation, and all that structure is there under Lorentz transformations. So I just wondered this, at least in the qubit case, one would be able to identify some kind of relativistic kind of observations there. I don't know. That is just a curiosity question.
Yeah, so I want to say, first, that's very interesting. And second, I just wanted to add another element of interest to your question that we haven't dealt with yet. When you talk about 2 qubits, then it's got a tensor product structure. And of course, tensor products and inner products have relations, and we haven't fully explored those. So in addition to the question of what the relativistic transformation would do, you know, possibly moving it out of the Hilbert space, your question also raises interesting points about tensor product that need to be explored.
Yeah, thank you.
So thanks a lot, Barry. And please do look out at the chat window, because we have a couple more questions which we have delegated to the chat window. So please do answer them, because we couldn't give them time for asking. So thanks once again to Barry and his co-authors for this very nice and interactive talk here. We will now move on to the second and last speaker for the day, Kishor Bharti. Kishor Bharti, are you with us?
Yeah, I'm around.
Kishor.
Yeah. Somehow I cannot like open like start the video because it says I need host permission to.
I think the hosts at IISER Mohali will do this for you. So while they do that, let me give a quick introduction to Kishor. Kishor is one of our bright young researchers who is going to give a talk now. Kishor works at the Center for Quantum Technologies, Singapore, that is CQT. He is concluding his PhD program soon under the mentorship of Vlatko Vedral and Leong Chon Kwek. He was a BSMS student at IISER Mohali with a focus in physics, and at IISER Mohali, he worked under the mentorship of Arvind. His research interests lie at the intersection of quantum computing, quantum foundations, and artificial intelligence. He has contributed 17 academic papers so far and has talked about his works at various international conferences. Adding one more to the list, Kishor Bharti. The floor is yours.
Yeah, thanks a lot. Thanks for the nice introduction, and it's always a pleasure to talk at my alma mater, IISER Mohali. I spent very important 5 years of my career there, and I thank IISER Mohali for giving me the opportunity to present my work. So the work that I'm going to talk about here, it's QAE and IQAE, blueprint for practical quantum advantage. So it's basically 2 papers which I have summarized here. So what you see here, this is Center for Quantum Technology, CQT. And this is the group here, Kwek, and also Vlatko, but not in the picture here. And then this is the guy like Toby, with whom a very good friend of mine, and with whom I have worked on these papers. And there are there are some follow-up papers which also came after that, which I haven't included here, but if somebody is interested, I would like to talk and discuss that work. So recently there was this experiment last year, the quantum supremacy experiment using a programmable superconducting processor. And what they basically did that, they had some sampling task which they performed on 54 qubit processor. Actually, one of the qubit didn't work. So at the end of the day, it was performed on 53 qubit. And the premise was that actually if you try to simulate this experiment on some super computer, then it will take 10,000 years or something. But they performed that experiment in 200 seconds. And in that sense, what they achieved was basically quite a remarkable feat. And it was called the quantum supremacy experiment. And there are opinions also written, different blogs and so on, where people have been talking about this experiment. And you can read this Scott Aronson blog where he talks about why Google's quantum supremacy milestone matters. Now one can ask, there are still debates going on, regarding whether the supremacy experiment was really done. In the sense that was supremacy really achieved or not, and it will take a lot of work and progress at the hardware frontier to convince people that as it happened with the Bell inequality experiment, over time people got more and more convinced. Okay, so the experiment which was done there, that was done for some kind of sampling task, but the task was not really useful. And one of the questions which is there that, though there is development at the hardware frontier, at the moment we do not have any kind of practical application of the existing quantum computers. And the problem is that as more and more industries and people from different disciplines, they are coming into this field, there is demand for some practical advantage in the near term. And as you can see, as John Preskill says, that a quantum winter there is a possibility of a quantum winter if we do not get any quantum advantage very soon. So then one can ask the question, what are the key problems where one should work on so that one achieves quantum advantage for practical use cases. And if you want to think about, some of the example problems to look at for practical quantum advantage, they are quantum simulation, combinatorial optimization, quantum chemistry, machine learning, and the list continues. But one of the problem which is very interesting and like has applications in like many of these areas is this problem of quantum local Hamiltonian ground state problem. So this problem is mathematically quite challenging. The problem is QMA complete. So you can think that, like QMA complete is similar to, like, I mean, we know the notion of P versus NP, and the problems which are, like the hardest problem in NP, they are called NP complete problems. So similarly, the quantum version is BQP, and among BQP, like you can think of like even for a quantum computer, this is a difficult task. So, but you want to have some advantage there. Like, I mean, if you want to like have advantage, then definitely you should, like select a problem which is like difficult, so that with respect to a classical device, when you like put them in race, you achieve some speed up. And since this problem has applications in so many areas, I mean, the speed up will be like useful. I mean, unlike what Google did with the experiment. I mean, their experiment, though that was, like great feat at the hardware frontier, but at the moment, as we know, there is no direct application of their experiment. So yeah, I mean, if we really want to have bypass the possibility of quantum winter, which has happened to fields like artificial intelligence, we need practical quantum advantage. So like to solve this problem of like to approximately find the like the ground state and ground state energy of quantum local Hamiltonian, the canonical NISQ era algorithm. I'm using the word NISQ. NISQ basically means that noisy intermediate scale quantum. So we are in some era where we do not have like fault tolerant qubits, like I mean fault tolerant architecture, and like we have only around 50 to 70 noisy qubits. And the question is, what can we do with what we have? And like we want to perform some kind of task on this NISQ, in this NISQ era. And in the NISQ era, the canonical problem, the canonical algorithm to solve the quantum local Hamiltonian ground state problem is this algorithm called variational quantum eigensolver. So like to get a glimpse of like to get an understanding of what this VQE is, this is nothing but the variational principle of quantum mechanics. So the variational principle of quantum mechanics basically says that suppose you want to find the ground state of some Hamiltonian, what you can do that you start with some ansatz, and the ansatz has some tunable parameters, and you know that by definition, like by construction, ground state is the minimum energy eigenstate. So if you try to tune the parameters, you will not find a state which has a lower energy than the ground state. So basically, you can use it to approximate the ground state and ground state energy. So, but the problem is that, I mean, like often representing quantum states gets difficult. And I mean, representation is one of the reasons why we are interested in quantum computation and quantum information. So in this very amazing paper by Peruzzo and like Alanas Guzik and others, in 2014, what they proposed that, let's use a quantum computer to prepare your quantum state. So you have some kind of parametric quantum circuit where you have some tunable parameters. So you have some theta. This theta could be something like, like rotations, like some X rotation, Y rotation, something like that. So you have some circuit which, like acts on all zero state, and you get this quantum state psi theta. For this ansatz quantum state, you calculate your expectation value of the Hamiltonian by like doing this ket and bra from the both sides. Now, this you can calculate on your quantum device by, for example, writing this Hamiltonian as a linear combination of Pauli and calculating expectation value of each of the Paulis, and from there, like inferring the expectation value. And then using some classical optimizer, you can tune the parameter. So the classical computer can tell that, like change theta to some another value, and then in this way feedback loop manner, you go here. But already you can see that though this algorithm is very interesting, amazing, but it has severe limitations. For example, you need this feedback loop. So like, I mean, for example, every time you need this theta to be fed there, and then on quantum computer need to prepare the state, then measurement needs to be done. And suppose you are doing it in some kind of, like, I mean, the way we do it on IBM, like we submit a job and it goes there and then again comes back. So normally to implement this algorithm, it takes like, a lot, like 3-4 days, like, I mean, even for simple 5-6 qubit Hamiltonians. Also, like, I mean, you see that the classical optimization like part is not well characterized. I mean, it's some non-convex optimization program because of the theta, like, I mean, that can be a non-convex set, and like, it's uncharacterized. So basically you cannot do some kind of rigorous mathematical analysis. So it's a heuristic algorithm which has been working in practice for some cases, but proving something mathematically becomes very difficult. Moreover, I mean, recently there has been like some work, like, for example, there was Google group which showed that like the way, for example, you update the parameters here by calculating the gradient of your loss function. But you would try to calculate the gradient, sometimes the gradient, you know, like, I mean, for large cases, it goes to 0. I mean, like using some property of the Hilbert space, you can prove that that's what they did. So basically, most of the random initialization, they suffer from this barren plateau problem. Like, as you will see, like, I mean, like there have been many papers recently, like including one paper by me also with my collaborator at Caltech and at CQT, who showed that, like, I mean, these problems are really severe and they are affecting you at many places. Like, for example, you can have barren plateau because of, you know, like presence of noise. If there is a lot of entanglement, that can also cause barren plateau. And then, like, recently there was a paper where they showed that even if you do gradient-free optimization, you cannot bypass the severity of the barren plateau. So it's a serious problem. Also, you see that, you know, the ansatz that they select here, I mean, it's very often chosen on the basis of heuristic, and there is not much information that goes from the Hamiltonian directly in the construction of the ansatz. So everything is very heuristic, and like at the level of expressibility, trainability, it suffers a lot. Yeah, but nonetheless, it was, you know, like it has been our best hope for quantum advantage in the near term. But the point is that it's like all these negative results recently has shown like, you know, I mean, concern that we should go beyond these VQE kind of algorithms. And so basically we need an alternative to VQE, and it's very important. Otherwise, I mean, like as I mentioned, like all those concerns of quantum winter and all, they are pretty much real. I mean, in 5-10 years, if we do not have any deliverable project, like then it can be a real problem. So so yeah, I mean, so what I am providing here is this QAE and IQAE, which is like a new generation of algorithm, which is beyond VQE and alternative to VQE. Also, I will show that, you know, like, for example, in here, like they showed that if you try to compute the, for example, in the VQE, the ground state of some Hamiltonian like sigma Z1, sigma Z2. So it's like on the first qubit, you have Z acting, the second qubit Z acting, and identity everywhere else. For such a simple looking Hamiltonian, you cannot find the ground state. Let's say like if you have like circuit depth high and so on. So it's really a problem. I mean, like, and we need to like solve it. And what I do here is that with my colleague, I use many of the ideas which were present in different papers, like very high impact papers like Nature and whatever, but they were doing it for, you know, like some cases where like either some complicated measurements were required, or it was heuristic, or I mean, so what I do that there's some paper ideas from computer science literature, some idea from like, you know, optimization theory literature, some idea from physics literature, and like, I mean, and by adding them, I come up with my co-author these two algorithms. So this is QAE and IQAE, and here I not only solve, like, I mean, some of the issues, I bypass some of the issues, and you will see that the whole framework is mathematically rigorous, and you can provide guarantees here. You can even tell when is your local minima, global minima. You can solve most of the issues, and I mean, I will talk about like what I mean and all. So let's now look at, you know, the same problem in like another framework. I mean, like another way to look at the same problem. So what I start with is the assumption that my Hamiltonian is linear combination of unitary. This you can do without loss of generality. I mean, for example, you can go in the unitary basis and write any Hamiltonian like this. Not only that, like for example, you can take, for example, this polytensor basis, and the polytensor matrices, they are not only unitary, they are also Hermitian. So yeah, I mean that this you can do without loss of generality. Also, I mean, like most of the naturally occurring Hamiltonians, like Ising model and so on, they are like they are of this format. So I start with this input model structure. Then what I say that I mean the second statement which I'm making is that if you are doing hybrid computation, don't use quantum state, use hybrid state. So what I have here is the classical combination of quantum states. So it's similar to this idea of linear combination of atomic orbital, which people have been using back in the past. So this is not actually a quantum state, but there are many quantum state chi1, chi2, chi-L, and so on. Actually, we'll see that I just need to prepare one quantum state. So I have linear combination of quantum state with some classical weight on them. So I have some register, like some notebook where I note alpha 1, alpha 2, and so on, like some weight something. And then what I say that the expectation value of the Hamiltonian with respect to this ansatz, like to calculate that, basically you put regular quantum mechanics 101 way, like Ket and Bra, and what you get is some expression like alpha transpose d alpha. Like, I mean, you can take a moment to see that. So basically, where this alpha comes from, from the Bra, and this alpha vector comes from the Ket, and this D matrix is this overlap matrix, which is like you have beta I coming here, and this ui has chi I from this side and then from this side. So you have something like this. Note that this is a quadratic expression. I mean, so not a bad expression. Now, moreover, you want the hybrid state to be a valid quantum state. So you put the normalization constraint there. So that was basically means that your zeta alpha inner product, that should be 1. So you will get alpha transpose E alpha equal to 1, where E is another overlap matrix. So this is the normalization constraint. Notice that what I have here is a quadratic program, a quadratic objective with a quadratically constrained, quadratic constraint with like a single quadratic constraint. So this is called quadratically constrained quadratic program, something called QCQP, and it has been like very nicely studied in the optimization theory literature. So already you can start bringing many of the guarantees from there, and start like you can see that it's already like a bit characterized than what it was earlier. And yeah, I will use this structure to do some kind of semi-different relaxation and say something about local minima and so on. So what I do that using the unitaries which define my Hamiltonian, I define this notion of something called cumulative k moment states. So I have set of unitary ui, and which, for example, you can assume them to be tensored polymatrices. You can also assume them to be, for example, any k local unitary or something. But let's say for the sake of clarity, I mean, or without loss of generality, also you can assume this unitary to be tensored polymatrices. So what you do that you have this set of unitaries, like those unitaries which appear in your Hamiltonian. Now, what you do that you say that there is some quantum state psi which some experimentalist can prepare. I'm putting no constraint on the psi. Like it can be, for example, the psi which Google prepared on their Sika mode processor. So you have some psi. Using this psi, you define this notion of something called k moment state. So this is how I define the k moment state. Like, I mean, I take unitaries from this set and I act k of them like ui1, ui2 up to uik. And the set of all such quantum state I call cumulative, I call k moment states. For example, one moment state will be u1 acting on psi, u2 acting on psi, u3 acting on psi, and so on. Two moment state will be u1, u2 acting on psi, u1 square acting on psi, and so on. The singleton set psi, this I call the zero moment state. So what I say that using by taking the union of all k moment state, I define this quantity called cumulative k moment state. And my ansatz is basically linear combination of cumulative k moment state. Already you can see that the way I construct my ansatz, in my ansatz, there is information of Hamiltonian is going there. So I'm like creating my ansatz in an informed manner. Now, once you understand this definition of this cumulative k moment state, I mean, it becomes easy to understand the algorithm. So algorithm is very simple. Actually, I can tell you that, we implemented this algorithm, and our algorithm, for example, the actual IBM quantum processor, it runs in something like, a few microseconds. On the other hand, if you try to run other algorithm, it will take you a few days. Now think like, like if you want to implement on this quantum computers, like if you are third party and you do not have access directly, you have to pay like $10 or $15 per minute. So in one case, you will have to pay like a few $1,000s. In the other case, like in our case, you can then do the whole thing within a few cents. So like, money wise also, if you think, there is like, advantage here. So basically the time advantage, translates into the money wise advantage. So your Hamiltonian is basically linear combination of unitary, and using your some quantum state psi that you have, you basically create your ansatz. The first step is basically happening on your notebook. There is nothing quantum happening here. It's not on your quantum computer or something. For this ansatz, you prepare your overlap, you compute your overlap matrices D and E on your quantum computer. This can be done very efficiently. In general, this D and E, the overlap matrix element, they can be complex numbers. So if you try to do it in a very naive manner, then you will need to compute the imaginary part and the real part, and for that you will need some control unitary, which I see papers online, people claiming that they are doing it in near term and so on. But I would say that near term is a bit abuse of I would say very abused term. No, our experimentalists do not have capacity to apply those control unitary. So in our ansatz, there is no need of any such control unitary or something. Actually, if you assume, for example, this U to be polytensor matrices, you can do it very efficiently. And I do not have much time, but you can talk to me personally or in the question answer section, and I can explain this can be done without need of any complicated measurement. Now, once you have computed this D and E, then you just need to run a quadratically constrained quadratic program like a QCQP. And if you are happy with the answer, then you stop it. Or otherwise, you say that, no, I want to improve my ansatz. But notice that between the quantum computer and the classical computer, it's totally disjoint. There is no feedback loop. So you can run this whole step, very parallelly, independently. And then after that, get the data and very peacefully calculate, you do your classical optimization and done. So in that sense, basically, we disentangle the 3 steps. And every step is you can analyze and look for quantum advantage and so on. So we are kind of studying these things. You will see more results coming in future. For example, we are using Google's data at the moment, and Google's data was useless for all practical purposes, but we are trying to say something meaningful from their data, and you might see some result, some paper on archive coming in next month or something. Okay. So now I will justify why do I select this ansatz. So to justify the ansatz, I use the idea of imaginary time evolution. So I say that any quantum state psi that you have, the only thing I demand that it has non-zero overlap with the Hamiltonian's ground state. This happens almost always, because it's very difficult to find 2 quantum states which are orthogonal. Even if you 2 Haar random states, they are they have some overlap there. So your quantum state psi, whatever quantum state psi that some experimentalist can prepare, I have that. I start with that. In the Hamiltonian's eigenbasis, I decompose the. It's all happening. On my notebook. I'm not actually doing it. I'm just justifying the ansatz. So I write my psi in the eigenbasis of the Hamiltonian, and it's written like this. Now let's apply this operator exponential minus tau h on my psi. So I know that for some tau greater than equal to 0, as I okay, so I write it, and then it's imaginary time evolution, and I have some quantum state gamma. This exponential minus tau h, I can, I can expand, and I get this, minus tau h power p by p factorial kind of term. You just plug it here. So you get this term here. Actually, a normalization factor of half is missing everywhere. So I apologize for that. But that doesn't matter really for our analysis. That's some constant. So now in the limit tau going to infinity, this gamma goes to the ground state. So you see that, we can already see where I'm going. So now you see that you take this operator and you express, an approximate, you write we define an operator OK, which is this matrix, but only up to, not up to infinity, but up to some integer k. greater than or equal to 0. Now this OK basically corresponds to sum of first k terms of exponential minus tau h. When you act on your, so using this OK, you define your gamma k like this. Again, a normalization factor of half is missing here. Notice that in the limit k going to infinity, your gamma k goes to gamma. So basically, I mean, you can see that this ansatz that I have, it's there are some, you know, like constants and so on sitting here, but it's nothing but, you know, the linear combination of cumulative k moment states. So these are the states which I, you know, like I used to define my ansatz. So as you give me more and more resources, I'm guaranteed to find the answer. But the point is that the problem is so difficult that you cannot even solve on a quantum computer. We just want advantage against some classical device. And for that purpose, it already works. And I mean, like, you cannot solve it because, I mean, complexity theory stops you. Okay, solve it like in the sense like without any approximation or something. So approximately you can solve it, and we are using the structure of the Hamiltonian to like justify the ansatz and so on. So already let's look at, you know, the Google's Baron-Plateau example problem which they had. That problem is trivially solved in our framework, which you can see analytically. So for example, you can start with the Hamiltonian, which is sigma z1 sigma z2. There is a single unitary here. So in your set of unitary, there is a single unitary. Your zero moment state is your any psi, for example, Sycamore processor, like what prepares psi, that psi. Your one moment state is basically your this unitary acting on psi. So this you have here. Cumulative one moment state is basically union of these two. Now you know that this unitary is very special. Like, I mean, U square is identity. So you have your two moment state is again the same thing. So it starts repeating. So your ground state here basically in this case belongs in a two-dimensional subspace. Now, no matter how many qubits you go, how many circuit depth you go, you will always find the answer. So you can analytically see that we always find the answer. And in fact, we ran it for, you know, like circuit depth 200, 300, and we see the answer and so on. Moreover, you know, like, I mean, we try some fun example like, you know, hydrogen and so on. And you see that most of the random initialization that you try, you get the answer. The only place where you suffer is that, you know, this a small line, which is, you know, like almost a set of measure zero. Why do you suffer there? Because, you know, the initial state has no overlap with the ground state. But you can always, you know, like, I mean, just move a bit epsilon away from there and find it. So basically, it always finds the answer. I mean, like, I mean, just as a demonstration, I'm showing you, like, I mean, we also try for, you know, some complicated cases like ring of disagrees or Ising Hamiltonian and so on. And which for any hard random state and something, you always find the answer. Notice that there is no Baron-Plateau in this framework by construction, because we are not changing the quantum state. We are changing the hybrid state. And for that, we are not computing the gradient. So because we were looking at the gradient, we had the Baron-Plateau problem. But in this case, we are, you know, like we are using this structure of the hybrid state that we have, and we are changing the alpha. So in some sense, like, you know, later we wrote some papers also on quantum assisted simulator, and there was some paper by Seth Lloyd, which we also dequantized for the, that paper was for differential, solving differential, nonlinear differential equations and so on. So, I mean, we are using these ideas of, you know, like density, we also define this concept of hybrid density matrix and so on. So I'm just telling that the ideas along these lines, they are very powerful, and we are seeing some promising results already. So yeah, I mean, we all like not only there the cases where imaginary time evolution fails to find the answer because of some symmetric constraint. In our case, because you take the linear combination, sometimes you can, you know, like get outside the symmetry subspace and find your answer. So yeah, I mean, we get the answer. Now let's look at, you know, the whole algorithm kind of a bit mathematically. So what we are doing, you know, like, I mean, we are trying to, this was the objective and this was the constraint. So using some Lagrange multiplier, you can define this Lagrangian, and you can calculate the, you can show that, you know, the Lagrangian relaxation that turns out to be an SDP. So that's an efficiently solvable problem.
Kishor, I'm sorry to interrupt, but you're not checking your other message. So you have around a couple more minutes just to let you know.
Oh, okay. Sorry.
Thank you.
Okay, so I mean, sorry that, you know, normally these talks like take a lot of time. So I would like just like to wrap up fast. So basically, you can do semi-definite relaxation. You can also prove like when your local minima, global minima. There is no need to do control unitary. And I mean, there are some guarantees and all that we like, you can say that this everything you can measure efficiently, like in polynomial number of measurements, you can get your answer. Moreover, whatever you can do in VQE, you can do in this framework. So basically you can merge VQE in this framework and you can subsume it. So this is a bigger algorithm which subsumes VQE, and VQE is a special case of our algorithm. I mean, so if I kind of talk like in terms of unsought selection, VQE is based on heuristic. Here it's systematic. Criteria wise, optimization program in VQE is uncharacterized in general. Here we have QC/QP. Random initialization in VQE leads to barren plateau. Here you do not have the barren plateau problem. Provable guarantee in VQE not possible in general, and here we have you can give guarantees and so on. So what I'm saying that we have a new generation of algorithm which bypasses most of the problems, and I have been giving this talk at multiple places and so on, and I believe that half an hour is not enough to basically convince everyone, but those who are those who want to talk, you can ask questions, you can ask emails, like more than emails I want like video talks, because it's easier to convince me and all. And we have been trying it, and you will see more results coming along these lines, and we are collaborating with different people like across the planet, and we are happy about it. So in future, we are trying to prove some complexity theoretic results, systematically reduce the number of quantum defining the unsoughts at a particular iteration, and demonstrating quantum advantage for practical use cases. So I will say that I'm more excited about this demonstrating quantum advantage than defending my PhD thesis, and I really mean it. So with this I will conclude my talk, and if you have question or something, I will be very happy to discuss with you, and if you have some interesting ideas, at the same time collaborate with you. Yeah, with this
Thank you very much, Kishor. I'm sure some people are definitely convinced by your results, but more so I'm very convinced by your enthusiasm. It was really a very enthusiastically given talk. We are sorry about the half an hour, but that is how it is with the conference. So the floor is open for questions, please. Do we have any in the chat? Or otherwise, please just raise hands as before. We don't have a raised hand as of now, or people are still absorbing. It's probably this half an hour. Yes, Sonel Malik, please. Oh no, sorry, it's Arvind now. Arvind, please unmute.
No, I just wanted to compliment Kishor because he was a BSMS student who joined here and kind of came here as a kid. It's good to see him finish his PhD and talk so enthusiastically about all these ideas. So very nice. Congratulations, Kishor.
Thank you, sir. Thanks a lot. I would say it was all shaped. It all started at ISAR, and I really feel humbled, and I would say gratitude for all the guidance that I received. I did multiple projects with you, and all this was shaped at ISAR and all. In fact, what we recently, I would say that I have a friend like Atul, and we work on weekends and all, and we both were working with Professor Arvind, and many of the papers we are writing at the moment together with Atul. And for example, along these lines of thought, if Professor Arvind can remember, in 2014 we were working on quantum simulation. So those ideas, at the moment I'm using it, and when I look at those slides and whatever, always good to go back, and I really feel gratitude for all the guidance I received at ISAR, which helped me come to CQT and further come up with these results and so on. Yeah.
So thanks, Kishor. Thanks, Arvind. Does anyone else have any further questions?
If you have a question, please ask. I would say I will be very happy to yeah.
Kishor, you may want to put your email ID in the chat window, because maybe people will think of things, because it was a lot to absorb, of course. So I'm sure they can just
Sure.
But one thing I really noted about your talk was when you said that the Google processor, all the results were useless. It takes some guts to actually say that. It was really very enthusiastic.
That is the case, right? It's a Sam. It's like people say this thing that there was this joke going around, that Google circuit basically simulated itself, and people are saying that my pot is good at boiling water, I mean, so I would say that, I mean, it's definitely, like I would say, interesting experiment at the hardware frontier, but I mean, it went beyond, like academic circles and reached to the place where at some point it became, like more than like just academic chatter, like, I mean, and that is the part, like, I mean, when I talk at conferences and all, I put it like, I mean, okay, this was some hardware achievement, but still, like, I mean, there was a recent paper which came by Yuan Dutch, I mean, which was also, I mean, recently published in PRX Quantum, where he says this thing that, like, what Google simulated was not some circuit, but a noisy version of their circuit. And one can always ask this question, that how much noise the circuit can have, so that the classical simulation, there is no efficient classical simulation, and nobody knows the answer at the moment. In the case of Bell community and all, at least, like they were like rigorous things and all proven, but I would say that in the computation domain, most of the things we are taking on belief and all, and there is not proper noise modeling available. Though people like Adam Harrow and John Knapp and others, they have been working quite hard in this direction, but at the moment we need a lot of work and like I would say like collaboration and to really understand what happened in that experiment. And you might see something coming from our side, like in a
sure. So that would be something we look forward to, and please retain this honesty and enthusiasm. So on that note, I think we don't have any further questions for you right now. So thanks a lot, Kishor, as well as, of course, Barry, for this session. So that's it from me. I pass it over to the organizers.
Thank you so much, Urbasi, and I thank both the speakers, Barry and Kishor. And if the sky does not fall on our heads, we'll see you tomorrow. So it's bye from us tonight.
Bye. Bye.
I thought it's not the sky which will fall. It will be COVID which will fall.
Yeah.
Yes, Arvind, on that high note, bye then. See you tomorrow.
Yeah, I mean, if one of the organizers tests COVID positive, then we'll have to think about something.
Shubh bolo is what we say in Hindi, right, Arvind? So please have a good night, and everyone should think positive and test negative. So bye then.
Yes, that's a good one.
Bye.
Yes.
Bye.
Good night, everybody.
Good night.
Good night.
Good night.